Hello everybody, today in this presentation I will try my best to cover another important topic from the series of databases, and that is DBMS and working with relations. So, our plan for today is that I will be explaining some key concepts as shown from this structure. Before we start though, I want to mention that this presentation does not cover everything that has to do with the topic, rather it's a brief look and also an introduction to what's available to learn from it. I assume that you already know some of this stuff and you'll probably need some summary of what's being read from the books. These books. These books. So, let's begin by defining what's a DBMS. Shortly, a DBMS is just a software that acts as an organized and control center for data. Imagine having records in scattered spreadsheets, Excel files, or raw text files. In our case, a DBMS organizes everything into one format, which is structured, which sits between the applications and the physical files, and it handles everything. A question rises when we talk about DBMS. Why should we learn about DBMS? How did we got here? So when I was talking about those scattered spreadsheets and raw files, the thing that I was pointing at was that whenever you work with files, the data there was isolated. And what I mean by that is that because each program independently defines and stores its own data, some of the information could repeat and be the same across different files. That is seen as data duplication and consistency issues. So how does the database approach solves the problem of data duplication and consistency issues? Well, the database management system is kind of squished between the applications and stored data, as we can see here from the diagram. So that opens the opportunity for application programs just to communicate their data requests and definitions directly to the DBMS. And that will be, of course, without the concern of applications to know how data will be stored on the hard drive. With that out of the way, we can summarize everything by just saying that the DBMS is just like a centralized model which acts like a record-keeping system that is keeping data duplication to a minimum. The structure of data files is stored in the DBMS catalog separately from the access programs, and we call this program data independence. In order for a database approach to be applicable, some level of data abstraction is required. That is because we need to describe specifications that are not included in the way of storing data. And the way we achieve that is with data abstraction. Data abstraction itself is just the process of hiding low-level physical storage implementation details while presenting a simplified logical view to the user. For example, instead of forcing you to know exactly which hard drive sector it's needed to store that information, the system abstracts that completely away. So what's a data model? A data model is just the tool used to achieve data abstraction. It is an abstract representation that defines how data is connected, structured, accessed, and stored within a system. There are few popular data models that are the hierarchical model, as we can see here, the network data model, and the one we're specifically looking at today, the relational model. To achieve data abstraction, database systems use a three-level architecture. Here we can see we have the conceptual model, we have a representational data model, and we have a physical data model. So let's quickly take a look at those data model levels. The first level that we have is the external level. So the external level shows only the specific data that is needed for a particular user or application, and it hides everything else. For example, a student sees their grades while an administrator sees tuition payment details. As you can see here, we have a view 1, which is just part of the arguments that are described with the whole schema. External view 2 shows the same thing but with the smaller set. Next, we have the conceptual level, which just shows what data is stored and how it's related to different data without worrying how it looks on the disk. And lastly, the internal level is the lowest level describing how data is physically stored on the hardware, including file allocation, indexing, and access paths. So as you can see here from the presentation, there is a class called staff, which is just a struct written in C, which has the same amount of attributes that are defined with the normal data types for a programming language. And we have a recursive definition of the same type, which is the next pointer to the staff record. So after we're done with describing what are the different data model levels, we're going to take a look at database schemas. So to prevent application programs from breaking whenever underlying disk structures change, database systems utilize the tree schema architecture. This tree schema architecture is described by those three levels. This three level setup creates data independence. In other words, data independence is the capacity of the database system to modify a schema definition at single level of its architecture without affecting other schemas or application programs at higher levels. So let's make a recap on what we have covered for now. So the traditional approach has data application dependency. It is prone to data inconsistency, and it is prone as well to data duplication. DBMSs are database management systems which organize data into single structure format. They sit between application and files. They handle everything, and the DBMS approach, applications make requests just to the DBMS. DBMS approach keeps data duplication to a minimum, and it keeps file metadata separate, which is data independence, and metadata is how files are stored and where on the hard drive. Data abstraction is a way of thinking about data and how it is described instead of how it is stored. Data model is a structure that uses data abstraction concepts to organize data. Data model and schema levels are physical, which are related to files and their paths. Conceptual, which is related on data abstraction and how data is stored with its relationships. And external is just the user views. Okay, so far so good. Let's continue further. What is RDBMS? RDBMS stands for Relational Database Management System, and it builds upon the relational data model where data is represented in the form of relations, or if we can call it, tables. Here is an image that shows, I think, a hierarchical DBMS and a relational DBMS in comparison. A relational database system is composed of relations which we call tables, and they are also called entities. Entity is a record of a type that holds certain parameters that define it. Here is an example of an entity called product and its representation as a class in C++. A relation has its components, which are described from the following image. Here we can see the domain, which holds the values for a single attribute. On this green top row here, we can see each attribute and its corresponding name. A tuple is called a single row under the attributes that identifies a single object of that relation. For each object to be uniquely identifiable, there is an attribute that is a subset of all the attributes, and it's called a primary key. Primary key identifies uniquely a tuple in the relation. Here in this slide we can observe some other relations that actually make up a database. We can see that some values in the cells of the tables are met in other tables as well. So this attribute here and this here, for example. More convenient way of denoting a relationship between entities is with the diagram in the bottom left corner here. Let's make it bigger for you. So here we have a box which represents a single entity. Its attributes are denoted by this oval, and a relationship between two or more entities is denoted by this rhombus figure. Here is another example of the same structure. Here we have a kind of the same structure but with mixed notation. You'll see what I mean by mixed notation in the upcoming slides. In this slide is described how entities relate to each other. For example, we have an employee-department relationship where the entities employee and department are connected by this dashed line, or the so-called participation. And there are some tiny connections, as you can see, also called cardinality, at each other of the ends. I won't go into much detail here on how and when the line is dashed or not, but I can only explain the relationships shown here. We have an employee entity and we have a department entity, and it's said that each employee is part of one and one only department, and on the other side, a department can have one or many employees. Here is an overview of the different notations that denote entity relationships and their cardinality to each other. That is the first most simple notation that I can present to you, and it's called Shen notation. There is a legend here, and there is also a detailed diagram of entity relationships, their participation, and their cardinality constraints. We continue on to the next type of notation, and that is called crow's foot notation. And as you can see, there is a legend again, and here is a comparison of the same diagram made with Shen and crow's foot notation. Here is Shen and crow's foot, and that is the legend of crow's foot. And lastly, there is UML. As you can see, UML stands for Unified Modeling Language, and it is heavily used when designing dependencies of classes and implementing different data structures. Here is the legend, and there are some terms described here. The first one is association, which is directly translated to implements, referring to simple class inheritance. The second is aggregation, and it just means that a class can exist on its own without depending on some other class. The third connection is called composition and denotes that a class is dependent on some other base class, and if the base class destructor is defined, so it is the child's destructor we will execute first. Diagram is the simple form of the previous slide from page 26. Here. That's just an example of a plan for implementing some classes in C++ here. So, we're approaching the end soon. So, as I said, I'm going to finish this presentation with some SQL examples and point out some important information about primary foreign keys. So, let's start with SQL. What is it? So, SQL is a standard programming language which is used to manage and manipulate relational databases. Instead of writing a whole algorithm to retrieve data, you can specify what data do you want to the database management system. Shortly, I can explain that it's some kind of logically divided to the displayed other languages that are DDL, DML, and the others, DCL and TCL. An example of DDL usage is the following. We have create table. And that's a DML example. We have to insert some values into the table and update a certain column. So we have arrived to the primary keys and foreign keys. Basically, primary key, as I said in page 19, is a subset of the set of attributes that uniquely identifies a row in a table. Here we have the case that each primary key is responsible for identifying a record for each relation respectively. Here for students and classes. Formally, we can say that in a relational database design, a foreign key is an attribute or set of attributes in a relation that references the primary key of another relation. There we have the relational representation of the diagram that I showed you in the previous slide from page 26. And there is a SQL script that makes those tables and joins them based on the defined constraints with the keys for each tables. And before we end this video, there is a raw SQL code for connecting two entities, departments and employees. And we finally made it to page 40 of today's presentation. I want to thank you if you stayed this far to the video, and I really hope that my summary from this presentation has helped you fill the gaps from the topic and harden your knowledge about it. I suggest you to follow me for more technical presentations and demos, which are going to be helpful for your learning journey. Go take the books and practice. Thank you all for joining me today, and I wish you all the best. Have a wonderful day.